So in the last video, we talked about the purpose of a scan. And a scan is to make our job easy, right? No one says that working in a laboratory has to be difficult or has to be hard. So the purpose of the scan was for me to go in and take a sample and put it into the instrument, close the door of the instrument, and give it a window to look for. I can make the window as large or as small as I want. The smaller I make it, the less difficult the instrument has, time-wise, to look for the data that I need as an analyst. And we brought up this idea of a spectrum, and we said that a spectrum could be something simple like this one hump, and it comes back down, and this is basically signifying where in the buffet line of the electromagnetic spectrum region that my molecule really enjoys. And on the report, on the computer screen, or on the receipt tickets that I get from the instrument, that is what we call our maximum wavelength. We abbreviate that with a Lambda Max. And on the report or the computer screen, it will list beside of that a number. And in this case, we just estimated it and said, let's pretend like it's 325 nanometers. So that is what we call our Lambda Max. Lambda Maxes can be found. You know, there are compounds that get analyzed all the time. So for instance, I can look up aspirin or I can look up caffeine, and in a reference textbook like the Merck Index or the CRC or the Sattler, those are the three common reference textbooks that we use in a laboratory, there's going to be a little bit of background about the compound. This is the compound, this is its structure, this is its melting point, this is its boiling point, refractive index if it has one. All of that is going to be provided. But within that description, you might see a Lambda Max, and that is how they list it in the Merck or the Sattler or the CRC. So now you know what that means and what that represents. So this will save me some time, right? If I know I'm analyzing aspirin, I can go to a textbook like that one, I can open it up, find aspirin, read it, find the Lambda Max, and it will tell me the number that I should be analyzing for the solution. Sometimes the laboratory experiments will tell me as well. So if I'm looking at a research article or if I'm looking at a lab experiment that I'm given or a laboratory practical, a lot of times they want to save you the trouble from the scanning, and they just tell you the number that you should be analyzing at. And then that way you can just go to that number and prevent the scanning option and save you some time, save you some energy, and get the things done a little quicker. However, scans, they're not simple sometimes like the previous one. So let's say I've got another compound and I run it between the same range, 200 to 800. I don't know anything about this compound, so I put it into the machine, I close the door, I scan it. That's the window that I scan. In the beginning of the buffet line, it might not want anything at all, so I see a flat line. And then it might get to a point where it says, you know, this is pretty good. I like this. I'm going to take some of it. But I don't really care that much for it. So it goes up and it comes back down. And then it goes through and it could find something else that it likes. And it could come back down to the baseline and then find something else that it likes. And then something else and something else. And it could have multiple humps on it. No one said that you just have to pick one thing off the buffet and eat it. The same thing's happening to the molecules. No one told them that they just had to pick one wavelength of the entire electromagnetic spectrum and be happy with it. Some molecules are happy with an assortment of different wavelengths. And sometimes on a scan, that's something that I could see. But the terminology is still the same. So I can go through and I can look at each top of the hump. The one here, There's one there. There's one there. One here. And one there. All of these are favorites of the molecule. And all of these have a lambda associated with them, right? That probably means that I could dial in to any one of those lambdas and probably get a pretty decent data analysis out of it, right? So sometimes when I go to the Merck or the CRC or the Sattler, sometimes it will list multiple lambdas for me to measure with, and that's why. Sometimes the molecules are happy with a number of different things on the table. However, there's still only one lambda max. That's it. The other ones are lambdas. But there is one overall lambda max that's still the favorite on the buffet line. And that is the hump that's the tallest. So this is really the lambda max, not the highest wavelength, right? This wavelength would be higher. This is around 790-ish, 795-ish, right? And then if I take a look at this lambda, this is going to come in maybe, who knows, 300, 400, 500, somewhere in there. I'll just estimate it. The lambda max is referring to the tallest peak on the spectrum. It is not the highest wavelength. And people get that confused very often. Okay? Just because this lambda is a higher number, that does not mean that it is the lambda max of the molecule. It's the highest peak that's on the spectrum. That is the lambda max. And the lambda max is the area that's the most sensitive, or the favorite of the molecule. Okay? And we like to dial into the favorites. We like to make the molecules happy. We want them to eat what they want to eat. So because of that, we try our best to make sure that is on the menu when we serve it up. And that is the definition of the lambda max. So sometimes molecules just have one hump on the spectrum. Sometimes molecules, though, they can have multiple humps on the spectrum. So this is a real spectrum that has been generated from an instrument. Notice that this molecule has been scanned between the ranges of 200 to 700. So 200 all the way to 700 nanometer. And along the way, there's multiple humps. So I see a hump here, and I see a hump there, and I see a hump here, and I see a hump there. On the computer screen and the software, it will tell you what each one of those numbers are at the very bottom. It will list every single what they call maxima. So you'll know exactly what wave numbers to use if you want to use any out of the assortment. However, if a question says, what is the lambda max? I look for the hump that's the tallest, and it's right here. And that number is the lambda max right there. And that means whatever number is associated with that peak, that is my lambda max. And it looks like maybe 273 here. Who knows? 270-ish, 280-ish, somewhere in there. So that is my lambda max. That is the favorite of all of the spectrum that I allowed it to scan, wavelength-wise. And because that's the favorite, that's probably the number that I want to use when I begin to measure this substance. So even though this spectrum looks a little more complicated, keep your bearings. And as long as you remember that, you'll be okay. Lambda max. All right, here's another picture. This is an old-fashioned receipt ticket print. that would be printed from a machine instead of a computer, kind of like a cash register, the old-fashioned cash registers or cash register calculators. And the same kind of thing's happening here, right? I mean, this was done January the 22nd of 2009, and it has a timestamp on it, so that way if I was working in a laboratory, they would know the date and time that this was analyzed. This was just a scan, that's all that it was, just to figure out what number I should be using in my measurements. Here it goes from 400 to 700. So this person probably knew that this compound was colored, and there was no sense in running in the UV portion, so they just wanted the visible portion, and that was it. So they allowed the machine to scan, and that's exactly what happened here. So they scanned, and they got a hump that was happening there, and it came back down. And then there was a small little hump that happens about here, and it comes back down. And on this receipt printer paper, what happens is that they label the peaks exactly where they are, instead of down below or off to the side. So this is 445. There's the peak. I come down. That's at about 445 according to the instrument, nanometers. And then there's another peak here that it likes, and that one's at 658 nanometers. Out of the two, though, its favorite is the tallest peak, so that's 445. And that is where I would want to make my measurements for this particular type of compound that I'm running. So, another view of a spectrum. This is kind of old school, back in the day. And this one is kind of new school, that's happening now on a computer. And it gives me the same type of data, just maybe in an electronic format instead of an old-fashioned pen and paper format. So that's where I'll stop this video. You now know how to analyze a spectrum that has multiple lambdas. Again, you need to take a look and find your lambda max, and that is the number that's the most important. So in the next video, we'll talk about this function called a goto. So this was scanning, and now we need to focus on a goto function, which is the most important function onto the machine.